Welcome, everyone. We're doing a webinar today on Revolutionize Your Workflows with RS2 Python scripting. I'm Dan. I'm joined by Will. He's going to appear in about a couple minutes. We're both software developers at RockScience. Before we begin, I'd like to mention that we are recording this webinar. It will be posted on YouTube in a couple of days. Additionally, if you have questions, there's a question box that you can type in, and we'll answer all those at the end of the webinar. So let's go. All right, a bit about RockScience. So RockScience is a global software company. We do civil mining and geotechnical software tools. We've been at it for about 25 years. We started as a startup, and now we're about 80 people. We're all over the world and used by about over 10,000 users. So currently, we're broadcasting from Toronto, our head office, but we do have an office in Vancouver, as well as additionally in Peru, Ghana, and other places, and we want to continue to grow, of course. Our motto, of course, is geotechnical tools inspired by you. So we're developing comprehensive, customer-centric, innovative tools. And this has led us to develop 20 tools, and one recent one just came out. All of these tools, of course, are connected in our RockScience ecosystem, all of which you can go from one analysis to another. If you have stability, you go to settlement, go to finite element analysis, et cetera, et cetera. Today, of course, I'm focusing on RS2. I'll talk a little bit about what it is, what the product is, and what's its applications. Then I'll talk about how Python scripting fits into this workflow, how it can benefit you. Will's going to come in and talk about how you start scripting in the RockScript editor or your own environment. He'll also talk about how you learn about our API functionality and the types of resources available for you to get going. I'll come back right at the end. We're going to do some live coding with some scripting to do some real-world problems. All right, so RS2 is a complete 2D finite element package. Really what that means is we can do a variety of static, dynamic, groundwater, and thermal analysis. The types of problems you might be able to solve would include the support design on the right. You have consolidation seepage, we have slow stability, underground excavation, liquefaction, and many, many, many more problems. And really how scripting fits into this is now you can programmatically control the R2 functionality using a well-known Python programming language. Now, Python has a huge welcoming community, a huge library of things that you can import into your scripts to really improve and automate those time-consuming manual tasks. Ultimately, we want you to improve your productivity and ensure that engineers across your company can carry the analysis efficiently and consistently. Our final goal, of course, is that we want you to be able to control multiple RockScience products in one script. That's our goal, and that will fit in greatly into our ecosystem that's already well-tuned to move from one product to another. So Will's going to come in now. He's going to talk about setting up the scripting environment.
Thanks, Dan. Okay, so we provided you with two ways to get your scripting environment set up. The first is to use our pre-configured RockScript environment. This provides you with Python and some common libraries, and it also provides you with a pre-configured code editor. It also comes with RS2. So when you download RS2, it will automatically be installed onto your computer. For those more advanced users, feel free to bring your own Python in your own code editor to allow for more flexibility. Let's start with how to start with scripting using the RockScript editor. So it's going to be very simple. You open the RockScript editor from the RS2 scripting menu, then you'll run the file. And this whole process is gone over in the Getting Started document. So I'm actually going to do it for you guys. So let's open up RS2. Okay, we've got it open here. And you'll see now that we've added this scripting menu, and you'll be able to open the scripting editor. Okay, now this is a pre-configured editor that you can just start writing code in. So let's start by opening the first tutorial. So I'm just going to open a file. Let me get the path to the first tutorial here. So we'll do the hello scripting one, hello scripting.py. Open. Okay, and Daniel's going to go through more in detail about what every single line does. But this is just to show you how easy it is to set up. So all you have to do is click run. So Python is already configured. It already comes with debugging functionalities. And it also comes with autocomplete. So you can see right now it's opening RS2 and also the interpreter. But yeah, you have access to things like auto-completion. So here are a bunch of suggestions. You have some debugging features, and it also comes with all of these libraries. So if you want to use NumPy, which is a very common math library, you can use that. Matplotlib, which is a very popular graphing library. So once you get your results, you can very easily graph it. And also comes with pandas, which will make reading from CSV files a lot easier. All this is provided for you in the RockScript editor. Now, let's go over, for maybe more advanced users, how you would want to set up your own scripting environment. So you'd have to install Python first. So that's bringing your own Python interpreter. You'd have to install our RS2 scripting library, which you can find on PyPy, which is where all the Python libraries are hosted. And you can bring your own code editor. So if you like Jupyter Notebooks, Google Colab, PyCharm, Sublime, Eclipse, whatever you want that supports Python, you can use. So I'm going to show you two quick examples. I have Visual Studio Code installed. And I already have the, some examples open. But some advantages of using some other code editors is, for example, this one has access to Microsoft's proprietary extensions, which allows for these pretty colors that you see. And it also has access to Microsoft's tool of third-party extensions that might not be available on the version we provide you. In addition, we can open up Jupyter Notebooks. So for example, let's go to download Jupyter Notebooks. Let's open this in a terminal. And let's write Jupyter Notebook. All right, here we go. Okay. So now we have our Jupyter Notebook running. Let's open the webinar one. And this is just to show you, generally with engineers, Jupyter is a very common framework to use. It allows you to basically run snippets one at a time. So if you're here, for example, I can run the first snippet. I can start the application. Oh, that's because I didn't close the other ones. This one. Start the application. Connect to it. Open a file. Get a material property. Change the Young's modulus. Anyways, Dan will go over this more. But all this to say, you can, you can use basically any Python code editor that you want to provide. Okay. In terms of resources to help you learn RS2 scripting, we've provided you with a reference manual. So if you want to learn something maybe about history queries, you can use the search. And basically, here's a function, get history query results, and it'll show you basically in which modules you'll need to search to find this functionality. And we also provide you with like code snippets. So I think this is the, well, let's do time query. This is a code snippet indicating manipulation of time queries. So you can click on this and it'll provide you with an example of us using time queries. And this is something that you can just copy paste and for easily get started with something that you want to learn. Second, we also provide scripting tutorials. This is probably the thing you want to start out with. Right now we have the getting started as well as one fully fledged tutorial. And those are the main resources to help you along your learning journey. So to talk about more specific real-world applications of scripting, I'm going to pass it back to Daniel.
Thanks, Will. All right, let's do some live coding. So we're going to start off with a simple modeler interpreter example. I'm going to show you the simple workflow that you can expect. and setup, and then how these workflows go into more advanced problems. It's, for example, if you're doing a civil problem, like changing the bulk spacing for an anchor sheet pile wall, or if you're doing a more of a mining problem, like you're doing the slope problem, slope stability analysis, considering spatial variability of the soil strength. So let's get into that. So I want to start off by opening the editor. We're going to start off with a new file, just so it's a bit more obvious what's happening. I'm going to go ahead and close. Here, we're going to reopen them anyways. I'll start off by writing out the comments that what we're going to do. These are not the line of code. These are just descriptions of what we're going to do. And then I'm going to do line by line, add the code one by one. So first of all, we're going to do importing libraries. We're going to say import libraries. We're also going to start the modeler. We're going to open a file, a model. We're going to modify the material properties. We're going to save, and then we're going to compute. So how do we do this? The first thing you want to do is you want to import the RS2 library that contains all the functionality you want to control the modeler. So in this case, for the modeler, you want to say from rs2.modeler.rs2modeler import rs2 modeler. You notice that as I'm typing, so for example here, it's starting to autocomplete or give me suggestions on things that might make sense for what you want to type. So if you hit tab, you're basically letting it complete it for you, and usually provides reasonable suggestions. The next thing you want to do is you want to start the application. This is like me opening RS2 modeler. So what you would do, for example, you would say modeler, or you would say rs2 modeler.start application. Now you notice it'll ask you for a port number. All you really need to know about the port number is that the number between 49,000 to about 65,000. And this port number is an ID used by the script to communicate through this ID port to the modeler to run the analysis, or run the function, I should say. So as long as you don't conflict with another modeler that's open with the same port number, you're not going to have a problem. So for example, if I just put 60,000 like this, and I go ahead and run that script, it's going to open up the modeler here. Now, if you want to check what port that modeler has open, you can always go to scripting, manage scripting server. It's currently running on port 60,000. So let's say I mistakenly try to run the script again and open another modeler on that port. You're going to get a warning saying port number 60,000 is occupied. So really, once you run it once, and if you keep the modeler open, you don't need to run it multiple times. So I'm just going to comment that out as we continue the script. So now you need access to the modeler. So you're going to want to create an object called modeler, and you want to say rs2 modeler port equals 60,000, which is the port that I just opened the application on. So now you have an object called modeler. That's when you can start to control the features of the modeler. For example, opening a file. You're going to need this object. So just to make it a bit clear what's happening, I'm going to put the code onto the left and put the modeler onto the right. Okay, so now if we want to open a model, we want to, first I'm going to grab the model location. So let's go grab this here. What we're doing is I'm giving it the full path to introduction to rs2.fez model. If you want to open this model, it's very simple. You can just say model equals modeler.open file, model file path. So what it's doing now is, if I run this, it's going to go ahead and use the modeler to open the model from this path that I gave it. And I created this model object. Now, every time you open a file, if you had multiple files, you're going to have different model objects. Each of those objects is what you're going to use to control things in that file or change things. For example, if I want to change the properties, so for example, in my material property, I have a till material. If I want to get this till material and make changes, I would need to get the material object from that model object. So for example, if we say material1 equals model.get all material properties, this gives me a list of all of the material properties in this dialog. So we only have one, so I'm just going to put an index of 0, meaning give me the first and only material property in the dialog, which is till. Now I can go ahead and start changing things. So for example, if I want to change the unit weight, I just go ahead and say material1.set unit weight material1.initial conditions, which is this tab, dot set unit weight 0.02, let's say, if we want to change it from 0.027. If you want to change the strength properties, it's a very simple pattern as well. You just go material 1.strength now, because we're in the strength tab. You want to specify that it's more coulomb. So you're going to say more coulomb. And then you want to set the, let's say, peak friction angle to 30. That's how you do that. 30. And then let's say you want to change the friction or the cohesion to, let's say, 0.001, let's say. So now if I go ahead and run that script, I'm going to go ahead and make those changes. So now we have a unit weight of 0.02. We have a strength of 30 or a friction angle of 30 and a cohesion of 0.001. So that's great. If you want to save these changes, very simple. We're going to use the model object again. We're going to say save. If we want to compute it, we're going to say model compute. Now if I go ahead and run that script, it's going to save those changes, run the compute file, or run the engine. Now we have a computed model that I'm ready to look at the results in the interpreter. All right, let's create another script just to run the interpreter. Of course, you can have them in the same script. There's no problem with that. I just want to separate them just to give a clear understanding of the modeler functionality and the interpreter functionality. So in the interpreter, I'm going to start again by writing some comments, and then we're going to fill in the gaps, fill in the lines of code. So we're going to import libraries again. Import libraries. We're going to want to start the interpreter. We're going to want to open the model. We're going to want to change the contour type to total displacement. We're going to want to change the stage, and we probably want to draw a query line. And we probably want to extract data from the query line. Okay, so how do we carry out each of these steps? So like I mentioned with the modeler, you need to import the modeler's library to run it. It's the same pattern. So from rs2.interpreter, rs2 interpreter, import rs2 interpreter. So these give you all the functionality to control the interpreter. And again, we need to start the interpreter in a port. So dot start application port. Now we use 60,000, port 60,000 for the modeler to just make sure it's not the same number. So I use 60,001. So now if I go ahead and do interpreter equals rs2 interpreter port equals 60,001. Now this interpreter object has access to the applications that's using port 60,000. So if I go ahead and run that, I'm going to open up the interpreter. So I'm going to keep that to the right, just so it's a little bit clearer as I go along in the script. So let's do the same thing. Let's open up the model. So I'm going to copy again the model path, same path. We're going to go model results equals to interpreter.open file model file path. So what this does is it'll do exactly the same thing as we did for, I got the wording here, so I should comment out the start application. So what I was saying is this line of code now will open up the model in the interpreter that we just computed, the introduction to RS2 FZ. Now you can start to control the things. And again, like I said, you have a model object that will control all of the things that you want to change. So for example, if you want to change the contour type, you would say model results dot set result type. Now you'll notice that it's going to ask you for a result type of type export result type. Now export result type is an enum or a flag that we have created to specify the different types of results that you can set. So what you're going to need to do is import all of these flags before you can use them. So you're going to need to go back to here and say rs2.interpreter.interpreter enums and import star, meaning import all of the flags from the interpreter enums file. Now, when you say export result type, you get access to all of the flags that correspond with the contour types. So we're interested right now in the total displacement. So I'm just going to go ahead and find solid displacement, total displacement. And if I do that and run the script, it'll change the contour type to total displacement. So if we want to change the stage, very, very simple. You say model results.set active stage. Well, I'm going to say the third stage. So if I run that, changes it to the third stage. Now it comes to more interesting things. What if you want to draw a query line underneath this load to do further analysis? So it's very simple to do. You just say model results dot add material query. You're going to need to feed it a list of coordinates. So each coordinate being a query point. So I'm going to feed it 5 points underneath that load. It's going to be -2, 4, -1, 4, 0, 4, 0, 4, 1, 4, and 2, 4. So I go ahead and run that. I'm going to draw a query line underneath with the total displacement shown of those queries. Now, if you want to extract that data, you're first going to want to say query line equals to model results dot get material query results. This gives you a list of all of the queries that exist in your model. In this case, we only have one query. So I'm just going to put index of 0, meaning get me the one and only query line that I drew. That query line contains 5 query points. So if you want to extract those points, you're going to need to write query results equals to query line dot get all values. This will give you a list of query results, each of them being a query point. So now you have a list, you can start extracting. So if let's say I created a total displacement list, total displacement values equals this, a list. For each query result in query results, I can then go ahead and extract the query data. So query result dot get value. And you notice here we also have access to coordinates if you need it, but today we just need the value, which is currently the total displacement at stage 3. And we're just going to print that to the screen just so it's a little bit obvious what I've done. So if I go ahead and do that, you'll notice down here we have 0.00978 printed. This is the first query point, total displacement. Second one is 0.0148, which is this point, and so on and so on. So now you can go ahead and extract that to Excel. You can export it. You can do whatever you need to do with that information. You can plot it, of course. So now that we have that, let's move on to how that applies to sort of more complicated cases. I picked civil and a mining problem, like I mentioned. So for the civil problem, so let me just close that here. So for the civil problem, I picked a excavation that you can find in our tutorials, which you have an excavation and you're designing the support to hold as you're staging the excavation. So what you might want to do is you might want to say bolts here and change the bolt spacing. Let's say change it to 3. You might want to rerun that analysis and then look at the bending of the wall or displacements and then try another design and try another design. So that manual process we can actually automate in scripting. So I just wrote a simple script here. If I just go ahead and close these. And I'm not going to go through all the details of the things, but you'll notice that you import a bunch of libraries, like I said in the beginning, in the other workflow. And the key thing to focus on is down here. We provide a convenient function that you can change the tieback out of plane spacing in a loop. And every time you change the spacing, you can save it as a different model and then compute that model. And now you have a set of models you can extract information from. So if I just go ahead and run the script, it's not going to do computation because that's going to take a bit longer. What it's going to do now is just output those 3 different spacings that I tested. So spacing of 1, 2, and 3. And it's going to go ahead and also change the contour type to horizontal displacement and stage 3 or stage 5, which is what I'm interested in. And now you can easily compare the 3 models in the interpreter. Additionally, I use the built-in matplotlib, which is something Will mentioned is included if you install our library, which allows us to plot the axial force, the shear force, and the bending moment of these 3 cases. And the great thing about this is if you need to make a modification to the base model, remeshing it or changing the material properties, you just need to rerun that script again. And now your engineers can focus on the analysis of the results rather than manually having to change things and spending time on that. So that's a very simple civil problem. What happens if you're looking at a more slope stability problem? So a simple slope might look like this. And normally what you might do is you might calculate the factor of safety of this slope. And you might say to yourself, okay, what about if we do a statistical analysis? So in slide 2, there's a convenient spatial variability option. What that means is slide 2 automatically generates various samples where these different colors represent a friction angle that's a little bit different based on location in the same material. So it could range from, let's say, 25 degrees to 35 degrees. And it automatically generates all these samples and calculates the factor of safety for all of these cases. Ultimately, what you want from slide is in the results, you can generate a histogram. And this histogram plots the factor of safety for all of your samples and highlights the ones that are below a factor of safety of 1. And now these 14 failed models, or less than 1 factor of safety, you can use to calculate the probability of failure. So 14 out of 100 means 14% probability of failure. So you can do this in RS2. And what you would need to do is, let me go back to this. So this you can output as a point cloud of XY locations and friction angle. Once you have that information, which can come not only from slide 2, but from a MATLAB script or anything else, you can go into RS2 and manually going to the properties, defining a discrete function, importing that point cloud of information to RS2 as a discrete function. Then you would have to run SSR analysis, get the SRF, the critical factor of safety, or critical SRF or the factor of safety, rinse and repeat for all of the samples you want to do. So you would have to go back and export more data, recreate a new model manually. Now with scripting, we can automate this process. And I've just written a simple script to do that. So here you have, again, quite a long script, but I want you to focus on just these key points. I wrote a function called update model material. What it does is it looks at all the data in a file location, and it automatically creates discrete functions to set into your model. Once it does that with one sample case, it saves that as a new sample, new model, computes it, and then the interpreter has a very convenient function called get critical SRF, which extracts the factor of safety. And now in a loop, you can do this automatically. You can go ahead and read as many samples as you want. So if I just run this script, again, we're not going to compute because that's going to take a bit too long. But what it will do now is, close these here. So what it will do now is it'll generate that histogram that we saw based on the 100 samples of RS2 model that automatically created. And now RS2 calculates that 11 out of these 100 samples have a factor of safety below 1 with a probability of failure of 11%. So again, the great thing about this is, let's say you want to remesh because the discrete function might be mesh dependent. Great, do that in the base model, and then you can rerun that script and let it run, and it'll output the histogram. Additionally, what you could do is you could go ahead and output the models that have a factor of safety less than 1. And now you can inspect the failure surface that is predicted by RS2, and also the properties or like the locations that are contributing to why these factors or these models are unstable. So that's sort of the power of automation using Python scripting. Okay, great. Everyone have a nice day and take care.